Thank you very much for the very friendly invitation. I knew that there is something like a superconductor. I never knew that there's also something like a super expert. I'm not all that cold though, and which hopefully also implies that you feel that you can ask questions all the time while I'm speaking. So my topic is electronic transport, and my mission will be to show you how you can use the electronic structure information that how to obtain you have learned in this workshop in order to make predictions for measurements of conductances and resistances. The emphasis in this talk is about such methods and situations where this transport theory, the transport information, will be gathered from ab initio methods, as I think is appropriate for this workshop. So let me first, before I dive into the methods, give some illustration where situations arise where these methods would actually apply and what type of information they could yield. So there is a set of experiments that is called mechanically controlled break junction experiments, where the experimentalists in some way achieve a situation where a molecule, for instance such a molecule, is contacted between the left and the right-hand side lead, and a current then is run through this molecule, and what experimentalists measure is the IV characteristic, so how the current depends on the bias voltage. And now this IV characteristics can be manipulated in many ways. So for instance, you can exchange the molecule in there, or you can pull at the junction, or you can push at the junction, you can put everything into solution, and so on. So there are many ways to play with these junctions. All of those come up with their individual IV curve, and the job of a theorist often would be to understand how these IV curves arise in the first place, and then how they change under all these experimentally changing conditions. This is another situation that you might be already familiar with from some other context. So I mentioned that I have a substrate, and on this substrate deposited would be a molecule, and then there's an STM tip approaching the molecule, and again you ask about how the current flowing through the molecule depends, for instance, on the distance of the STM tip to the molecule or on the bias voltage. So actually, incidentally, this type of experiments are being done here in Berlin, for instance, in the group of Katharina Franke, and that's a very nice set of experiments that she's doing. And if I wanted to understand those, then the methods that I'm going to explain to you could be very helpful. Not only will they be helpful in the context of molecules, but also more generally, you could use them in order to, for instance, understand transport through such molecular films. This is a zigzag nanoribbon, as they can nowadays be produced relatively in a controlled way on substrates. And again, you can contact those here and there, for instance, and you can ask how the current flows through such a ribbon, and the methods will then answer for instance, about the IV characteristics, but even more than that, you can also use them in order to describe in detail how the current actually moves through this ribbon. The lecture is divided in several parts. So the first part is maybe for you the most interesting part. That's the one where I'm trying to explain how those transport methods that are relevant to understand these experiments, how they relate to those calculations that you have been doing already over the last 10 days or so. And then I would like to give you two more recent applications so you can see what you can do with these methods in practice. Here I will focus not so much on the physics in these experiments. I will be brief about it. Mainly I use these examples as an illustration for what these methods can do for you. And then in the end I would like to comment briefly on those things that I'm leaving out in this talk, and as you can imagine I'm leaving out quite a bit. This is again just to provide you with a certain impression of what other things can be done at the moment already, and I will conclude with a brief outlook about those things that I would like to be able to do in the near future. So here is what you get from electronic structure calculation. This again is the molecule, as I was showing you before. This is a contact, this is another contact. We would like to drive the current through this. And now if you use such a setup in your DFT calculation, this would be a set of atoms that simulate the gold cluster, for instance. Gold is a typical electrode element in this business. then there could be a gold cluster over here and a gold cluster down there, and you have a molecule that you have electronically relaxed in between these clusters, and you can then calculate wave functions, for instance, on DFT basis, and I'm sure that most of you can do this a lot better than I at the moment. So you know what I'm talking about, right? These are, for instance, typical cone-sham orbitals. And now the method that I'm going to introduce for you is a method that takes these wave functions together with the energies associated with these wave functions and converts them into information about the current voltage characteristics. Here is the basic physics that's behind the method that I'm going to introduce, and it's really basic. So you can see this is a one-dimensional example where we have an electron coming towards a barrier, and then you know from your undergraduate quantum mechanics that at this barrier the electron is being reflected or transmitted with a certain reflection or transmission coefficient R and T. And then you also know that the probability to pass the barrier has to do with this transmission coefficient squared. So there is a relation between the energy of the particle and the transmission coefficient. Not surprisingly, if the energy is high, the transmission probability is large. If it's low, then the transmission probability is low. And actually, what the characteristic object here is a wave number of the electron, k, and it's related to the energy of the particle via such a dispersion relation. So here you immediately see a relation between wave function, here a scattering state that enters from the left, and the transmission probability that eventually, as you can easily believe, will be related to the conductance of the system. Large conductance means large transmission probability. Low conductance means low transmission probability. So this is not quite a molecule, right? This is just a barrier. So for the molecule, for a very simple caricature of the molecule, I imagine that I have a contact here, which is like a barrier, a contact there, which is like another barrier, and in between is a molecule. And this is the reservoir left, and this is the reservoir right. And now we again ask, how does a molecule, an electron that enters from the left-hand side, go through the first barrier into the molecule, go through the second barrier into the right-hand side reservoir. So now the difference as compared to the situation with a single barrier is that in the presence of two barriers, I get transport resonances. So these transport resonances just reflect the fact that the barriers, if they are very high, they support wave states. Over here, they have a discrete spectrum. And now whenever the wave number that enters from the left-hand side is commensurate with the wave number that allow for this distance here in the presence of the barriers, then I get a high transmission, otherwise it's small. So I have a transmission probability, TFE, as a function of energy that looks like this. There's a resonance over here that reflects the first state, eigenstate of this barrier, isolated barrier system. The second resonance reflects the second eigenstate, and so on. So these resonances have an energy position that's reminiscent of the energy of the eigenstate of this barrier. And then they also have a width. And the width just tells us about the probability that the particle, if it sits in here, eventually tunnels through the left or to the right electrodes and this goes away into the reservoirs. This is a typical structure of transmission functions as we will also find them in molecules. So these molecules have states. They have molecular states in vacuum, and now we couple the molecule to the leads, and then these states couple to the leads. So I will get resonances similar in the vicinity of the original eigenstates of the molecule, but these resonances are broadened, and the broadening reflects the coupling of the molecule to the contacts. So this type of curves we are actually after in order to understand the transmission probability and then also the conductance of the molecule. And our task from ab initio will be to calculate the energies at which these resonances appear together with the width of the resonance. Reasonably transparent procedure, I hope, for you. Now, the typical shape of these resonances is of this Gaussian type, of this Lorentzian type, and again, here the parameters that we have to find, namely the position of the resonance together with the width, enter now in a more quantitative way, and these are the ones that we want to calculate. There's one instance that we need to take also into account, slightly more complicated, not much more, but usually we don't have actually the single one-dimensional situation. We have usually a situation where the wires are not just one-dimensional, they have a width and a height, let's say, so they have several dimensions, which means that the characteristic quantum numbers of the scattering states that enter the molecule and then are being reflected or transmitted are not just characterized by a k, by a wave number. they also carry transverse eigenmodes, and these just reflect the fact that the wires have a finite width, and so within this width, I can be even in a transverse state that has no node or one node or two nodes. There must be a degree of freedom in the system that reflects the width of these wires, and that's actually the number of transverse modes in this impinging wire. That then leads to a simple modification. So now we can have scattering scenarios in which I come in with a certain wave number and a certain nodal quantum number here. Here it would be, for instance, 0. And then I can be transmitted into another state that has the same nodal quantum number, or I can be transmitted into a state that has a different nodal quantum number. Same thing with reflection. So now my transport formalism needs to take this into account. Strictly speaking, then the transmission coefficient for going through the barrier is no longer just a number that depends on k. It is a number that depends on n being the number of nodes here, and k. So it's t sub n and k. So then the current can be easily calculated. There's the transmission probability over here. That's the probability to scatter from an incoming state n prime into an outgoing state n, both with energy E. That's modulus squared, and then I sum over this. This is a total transmission probability, hopefully very transparent when you look at this picture. And then I need to convert this transmission probability into a current, and that I do in a very simple way. I'm going to say that the situation looks a bit like this. So there's a left-hand side reservoir and a right-hand side reservoir. I have a bias voltage, which means that the chemical potential left and right is different from each other. So that means there is a window of states where particles impinge from the left on to the barrier, like this. They come from here. Then they go through, and when they go through, they find empty states, so they can actually go there. This is a possible transport path, so I get a current from the left to the right. While if the energy of the particles is below this value, below the chemical potential on the right, then they impinge over here. They try to go through the barrier, but unfortunately everything is occupied here, so they cannot really go there, meaning that the current flows only within this voltage window. Probably not very surprising. So when I calculate the total current, then I sum the transmission probabilities over all energies, and only I take those energies into account that are sitting in the transmission, in the bias voltage window. One immediate consequence that we can see here is already the following. If the bias voltage is very small, so if the chemical potential of the left and the right-hand side is almost the same, then meaning it's almost like the equilibrium chemical potential or the Fermi energy, then the current is proportional to this difference multiplied with the transmission probability at the Fermi energy, and that's actually what we call a conductance in proper units. There's one little trick. The transmission probability can be written like this, as I just explained, and now this is actually a trace over T and T dagger, and the trace is to be taken over this channel indices, these transverse quantum numbers, so that's why I wrote there, this is the trace to be taken over the transverse quantum numbers of the left-hand side lead. And that leads to a certain complication, and that's the only point where now theory needs to enter in a bit more advanced way in order to deal with this situation. Let me try to explain what the problem is with this formula, nice and transparent as it is. So this formula refers to the degrees of freedom of the leads, of the reservoirs. Now the reservoirs are really, really big. The reservoirs are something like 10 to the 23 gold atoms, really macroscopic. And now it's not so easy to do a DFT calculation with 10 to the 23 gold atoms. Would you agree with that? It's really a challenge. So most people, except maybe Max Planck, would say we cannot do it. So and for most people, we need to invent something different. So we cannot directly use this formula. What we can do is something like this. As I explained before, I have a molecule. I have electrodes sitting over there and over there. And then I can study the eigenstate, the Gonsen state, let's say, of the system. I can study how they change if I make this system bigger and bigger, meaning I add more and more gold atoms on the right-hand side. But I really cannot go to 10 to the 23. So I cannot explicitly deal with all these degrees of freedom to the lead. I need to find some implicit way to deal with this. And what people then do, and what I also do all the time, is that instead of this formula, I use a closely related formula, which is this formula. There's a transmission formula, a transmission probability again as a function of energy. Now it's again a trace, but the trace is over the degrees of freedom of this extended molecule plus extension in the leads. It is not about the Hilbert space in the transverse of the leads. It's only the Hilbert space that I can deal with and not the Hilbert space that I cannot deal with. So in this way of thinking, I encounter new objects, this gamma, this G, and now I need to tell you what this gamma and the G is and how these objects relate to the original objects. So here's what the G is. So G is the Kohn-Sham Hamiltonian of the DFT calculation that you maybe have been doing on your computer. And then I subtract two matrices, sigma L and sigma R, and those matrices massage the corresponding Green's function of the Kohn-Sham system into such a way that if I take the Bayer Green's function, which comprises only this, and then I subtract the self-energy belonging to the left and the right-hand side lead, then what I actually get is the Green's function of this object in the presence of all the other atoms. So that's important. So I have a trick, a theoretical trick, how I can convert the Green's function of this system in the absence of reservoirs into the Green's function of this system in the presence of reservoirs. And the trick is to take the Bayer Green's function, absence of reservoirs, and now subtract two self-energies. So these self-energies must somehow deal with these leads, and they do this in the following way. So the self-energy here is actually an object, and now unfortunately one cannot see anything at all, so I apologize for the choice of the colors. So this self-energy is actually something simple. It is the Green's function of the reservoirs multiplied with coupling matrix elements that connect this, for instance, side with the reservoir side mu, and then there's two of those, meaning I hop away from the molecule into the reservoir and back again. So this kind of thing will be illustrated a bit later so that you can see what type of physics is behind it. And so you can also see that this can be approximated in a super simple way so that we can do nice calculations for extended systems, even though explicitly we only deal with this extended molecule and not the leads at all. Let me come back to this in about 3 slides. I rather now would like to get you some confidence into this formula by just using it in a very simple situation where I imagine that I have a molecule with only one state. So if I have only one state, then the trace here over the Hilbert space of the molecule is actually a trace over only one state. So these are all numbers. I can then use simple expressions for sigma. Sigma is actually I gamma. So in other words, gamma is the anti-Hermitian part of sigma, just a number. I introduce this object. Sigma is just the sum of these two anti-Hermitian parts. Then I plug this into the Green's function, which then eventually leads to a shape for this equation of this type. It's just G times G star, which then essentially gives rise to this Lorentzian shape that you saw already before. So hopefully this kind of little consideration strengthens your faith into this formula and that it is quite reasonable. In fact, it is more or less like this. So once we accept that the transmission function is a Lorentzian, then we can decouple it into two parts like this. It's a product of two of those. And two of those then are being promoted to be matrices, and then we get that formula. It's not so difficult at all. Good. Now let's go back and see what we can do with this, and then I tell you in better detail about the self-energies. So here's a typical example that you could work out in order to make use of this formalism. Let me not really focus on all of those molecules. Let me just give you this one, and then let me tell you what you can learn from this formalism. So the red and the blue molecule. So the thing why experimentalists were interested in measuring the transmission of these molecules by self-assembling them in such a film and then measure the IV characteristic was that they wanted to study what is the effect of this oxygen atom over there that's added to this molecule as compared to this molecule. And what's seen experimentally is that in these films, even though there's a large distribution of conductances, if you do this for an individual film, you need to repeat the measurement many times. Then you find a distribution of conductances. And what you can see is that the blue distribution corresponding to this molecule has a much, much larger conductance than the red distribution corresponding to this molecule. So please be aware of the fact that this is a logarithm of the conductance over the number of counts. So this is really a difference that is from -5 to about -8 or something like this. So it's several orders of magnitude difference in the conductance. How can we think about this? And that was then what was to be answered by these ab initio transmission calculations. This is a result of such a calculation. And what you can see here is a blue line over there. The blue line corresponds to this molecule, which is a large transmission. And then there is a red line that is sitting over here that corresponds to the red molecule. And you can see a typical structure. So there's two resonances sitting over there. These two resonances correspond to the isolated molecular states that I was promising to show up. The HOMO, highest occupied molecular orbital, and the LUMO, lowest unoccupied molecular orbital. And then there's a shape in between these resonances, and that's very different depending on whether you look at the blue or at the red trace. In particular, the red trace has this very funny behavior that is not at all looking like a superposition of two Lorentzians. It's just looking like this, whoop, it goes down and then it comes back up again. And this dip here is the reason why the red is so much below blue. And now the origin of this dip, that's something that could be clarified with these ab initio transport calculations. To cut a longer story short, in the end, what it boils down to is that there is a quantum interference effect. Namely, you have here a pathway through the molecule that goes directly through, while here you have two pathways. One pathway goes like this, and another pathway goes like this. So it first goes here, then it enters the oxygen, then it will go back. And these two pathways, the direct one and the one crossing the oxygen, they interfere with each other in an in a negative way, and this negative interference eventually leads to this type of dip. That's something that was not known before, and these, my colleagues have been able, so Christian Tügesen in particular has been able to clarify this by this type of calculation. These dips here, these are Fano resonances. They are not at all rare in these molecular transport experiments. For instance, this would also be expected if you have a different type of molecule, very different type of molecule, like a C60 molecule. There you would also see that there are these very sharp resonances downstairs, which suppress the conductance. And actually, the suppression has also been seen in experiments. You should not get the impression that the only thing you can calculate with the transport formalism I'm presenting to you is a transmission function and the IV curve. You can do more. You can also calculate things related to thermal transport. This is a very busy slide. I'm not going through this at all. I just wanted to tell you that in experiments you can also measure, for instance, the Seebeck coefficients. Seebeck coefficients tells you the following. So suppose that we have two reservoirs at two different temperatures. Then there's also a current flowing through the system, but only until the charge on the right-hand side accumulating annihilates the current flow through a counter potential. And now you can measure for a given temperature gradient what would be the counter potential. And the coefficient that comes out of this is the Seebeck coefficient. And now you see the Seebeck coefficient is essentially the derivative of the logarithm of the transmission curve. So we can also calculate the Seebeck coefficient. And that's then something that again can be calculated compared to experiment. And this works usually very, very well. So this transmission type of formalism that we talk about, I think is very powerful, for instance, in this field of molecular electronics. So here, as promised, one step back to understand better what the structure of the self-energy is all about and to give you better trust into this formalism. So I will not go now technically. I will go and try intuitively to explain to you what the self-energy actually does. And you know what? In principle, what it does is not so different from the self-energies that you have been learning about already in the talk by Patrick Rinke. So self-energies somehow take into account physics of baths, and that's not so different here from the case where the electrons are their own bath, and then self-energies describe the effect of an electron coupling to the bath of all other electrons. So here the effect with respect to transport. Imagine we have a molecule, green dots, and the molecule is sitting in between reservoirs, left-hand side blue, right-hand side blue. So we have a charge, let's say a wave packet at time t equals 0 sitting on the molecule. And now we would like to understand how the wave packet evolves in time, and that's interesting for us because the leakage rate, the rate with which the wave packet actually gets lost when it runs into the reservoirs, that leakage rate is interesting because that's the gamma, for instance, that enters the transmission formula. So let's see what we do. We propagate the wave packet in time, and if the time is not too long, then the wave packet just propagates in a way such that as if these electrodes were infinite. Now, in our calculations, they are not actually infinite. We only have a finite number of blue dots. And if we would now really do this propagation on the extended molecule, then at some point the wave packet would actually hit the walls, meaning the outer sides of the gold clusters. And once it hits the walls, it's going to slash hands and forth, which means in this finite size system, I cannot very well investigate the long-term dynamics of the wave packet. That's not a surprise for anyone, I don't think. And our question is, how can we go ahead and still use finite size systems and still learn something about the long-time dynamics of wave packets? And here's the trick. If we have a finite size system and this here reacts like a hard wall boundary, I get these cavity modes, slashing Hansen 4, they are the problem. To get rid of cavity modes, what I can do is I can introduce absorbing boundary conditions such that once the molecule reaches outside here and there, then the amplitude of the wave packet is just swallowed. Particles, quote unquote, vanish over here, they don't go back, and then I can very nicely study the dynamics of the wave packet in here, even in a finite system, as it would happen if the system would be infinite. So the buzzword is absorbing boundary conditions. And now if you have a self-energy that has an anti-Hermitian piece, gamma, then that anti-Hermitian piece destroys the Hermitian/unitary time evolution that you would have otherwise, and in that sense can be understood as an absorbing boundary condition. So that is the physics of this gamma. Once we understood this, we can then say, okay, so let's introduce absorbing boundary condition also in this transport calculation. We take a very big extended molecule. We just say that at the outer edges of the extended molecule there will be absorbing boundary conditions. In other words, the self-energy will look very simple. It is just a diagonal matrix in space with a prefactor. This is the damping rate. And to make it complex, I put a complex I over there. We put it into the calculation. And then this calculation for big enough a molecule will do exactly the same thing as I would get if the system would be infinite. So here's a check of this. The main contributor to the AITRANS transport module was Alexei Bagrets. He did many of these checks. Here the check is for the following arrangement. So we have an extended molecule, upper electrode, lower electrode. The shape of these electrodes can be varied. We have a library of different electrodes. We can make the size bigger and bigger. And now what we check is how the transmission through this molecule looks like for an increasing size of the electrodes. And what I'm trying to convince you of is that if we make it big enough, then the simple model for the self-energy, physically very transparent, gives us a nicely converged transmission function. Let's start with something small, so 22 gold atoms on either side. That gives the red line. You see a transmission curve that looks like this. And again, we resolve several of these molecular resonances over there. Now we enhance the size of the electrodes. We go from 22 to 33. And what we can see is that we no longer have the red trace. We have the green dashed trace. And what we get is, oh, okay, the result still depends on the size of the electrode because I get this huge shift here. But now I go from 33 to 55. That gives the blue line. And then I go 82 and 101. And what I see is that I get a better and better convergence about a curve that looks about like this. So that's exactly what I was trying to tell you. If the system becomes bigger, then the simple model for the self-energy that I was advocating before becomes applicable. The results are independent on what I actually do then with it. And that justifies why this method actually will be precise. It will be accurate in the limit of large electrode sizes. So this little method we are going to use later in the transport calculations. And every once in a while, we convince ourselves that the electrodes are big enough in order to get converged results. I should not leave you with the impression that you really have to rely on this simple model. You can also go much more accurately. You can actually calculate an exact self-energy if you want to. We do this, for instance, when we calculate the transmission for this strip. This then goes assisted by some kind of recursion method. This is called the decimation method. You can also do this. It is more tedious. In some cases, it's over necessary to do this. Not so much for the molecules, more for these graphene systems, which have a low density of states at the Fermi energy, and for that reason are a bit tricky. So that was just a line. Now I would like to continue with my examples. I was already giving you several ones, and now I go more slowly in order to see how a practical calculation using this formalism would actually be done. And what you will see is that it's not very different from what you did before all the time anyways. So here's my motivation for this example. So we have a collaboration with Lata Venkataraman at Columbia University, and she measures molecules in these break junctions arrangements. So we have this left and right hand side contacts. And in between there are molecules. Here it's a simple molecule. It looks a bit like an alkyne. She did a lot with alkynes. This is actually more interesting for us right now as a silane. Silane is an alkane where you replace the carbon with a silicon atom. And what she observes is that now there's a certain hierarchy in terms of conductances. The conductance grows from here to there. For instance, if you use these linker groups, they contact the molecule with a gold. So this is an amino linker. Then the conductance is relatively small. However, if you use sulfur linkers, then the conductance grows. And that's then something that one would like to better understand with these ab initio calculations. Specifically, we wanted to understand the following observation. So what you see here is again a distribution function of transmissions as measured in this experiment. You see a yellow and a kind of grayish distribution. The yellow distribution is when you use sulfur linkers with gold contacts, and the grayish is when you use sulfur linkers with silver contacts. And you see that with the sulfur linkers, the gold transmission on average is significantly lower than the silver transmission. However, if you change the linker group and no longer glue the molecule with sulfur, but you now glue it with these amino groups, then somehow the trend is reversed. So then gold has a larger transmission as compared to silver, and we wanted to say something about this. Here is what you then do in order to address such a question. So you could start with such a molecular arrangement in the gas phase. You attach one gold atom here, one gold atom there, and then you relax the structure. By the way, I apologize for the not so good quality of these plots. That has something to do with the fact that this is very recent research, and I just pulled everything out of the draft that has been submitted only yesterday. So I hope that that's still digestible for you. So we have this thing relaxed in the gas phase. And then after relaxation, we just add the electrodes, left and right-hand side electrodes to this arrangement. And then we do the calculation as mentioned before. We then have a DFT calculation for the full thing. We extract the Cohen-Sham Hamiltonian. We subtract the model self-energy, sigma L and sigma R, as explained before. We invert it in order to get the Green's function. We plug all of this into the transmission formula, gamma G, and calculate T of E. Very straightforward. And that we do now for the amino linkers and for the sulfur linkers, and we do it for different electrode materials, gold and silver. We, in this case, actually means never me. We means always a PhD student, a very good one, Maria Camarasa, and her husband, who happens to be her PhD advisor, namely Daniel Hernan Gomez. Yeah, so this is what we get out of these calculations, or what you also would get. So if you just would do the DFT proper, so you find states, molecular states. This would be the HOMO, for instance, for the amino linker in the presence of gold contacts. This is the LUMO, and this is the same now with silver contacts. And now what you can see already without actually straining your eyes too much is that this orbital, this HOMO orbitals, hybridizes a bit better with the electrodes as compared to the same orbital when you use silver electrodes. And this a bit better hybridization, that's something that now will be translated by the transport formalism into a transmission curve. Let me show you how this looks like. So here's the transmission curve. We get two curves, one for gold, one for silver, and they are shifted with respect to another. I will comment on the shift in a second. Here you see a pronounced resonance for the HOMO. Here you see the same resonance for the LUMO, and then same here and here, just shifted. Let's focus on the HOMO, which is this guy, and let's have a look at this. You see that's relatively broad. If you now go to the LUMO, which is this, and we look at the orbital over here, the orbital does not hybridize so well, and what you can see is that this is a bit more narrow as compared to here, and that's exactly what you would expect for these type of orbitals, as it should come out of the transport formalism. Same thing now for the silver. Silver HOMO resonance looks like this, and like LUMO resonance like this. These are the orbitals, and what you can see again is that this orbital hybridizes a bit better with the electrodes as compared to this, and for that reason this is a bit broader than the other. I think all of this is quite transparent. There was a remark about the shift. How can we understand the shift? That's easy in this particular case. Silver and gold have two different work functions, so that the alignment of the HOMO with these work functions is shifted by the shift in the work functions. Since this is E minus E Fermi, we expect a shift in the transmission curves that should be roughly of the order of the work functions, and if you look at the numbers, then it actually is. that was fine. So here we understand now for the amino linkers, the transmission of gold is significantly larger as compared to the transmission of silver. That's consistent with the experimental findings. Now we play another game. We replace the amino linkers by sulfur linkers, and then we see something funny. Namely, in the presence of sulfur linkers, there's a spike over here in the silver curve, and only in the silver curve, not in the gold curve. And that spike is relatively close to the Fermi energy, and it lifts the transmission of the silver curve quite a bit. So that spike is ultimately responsible for the enhanced conductance of the silver electrodes in the presence of sulfur linkers. And one can trace back where it comes from. This little spike over here has to do with what we call a gateway state, which is a molecular state that sits right on the linker group and that can mediate better the transmission compared to the HOMO, just because it sits much closer to the Fermi energy. So silver has such a gateway state, and that shifts the transmission, and for that reason, there can actually be an inversion. So our numerics almost produces the inversion, and actually depending on the functional, sometimes it does. Here we chose a function that doesn't quite do this inversion. Why doesn't it do it completely? Well, that has to do with these DFT artifacts of level alignments that we have learned about, for instance, from Patrick Rinke yesterday. So we are quite content that we actually see qualitatively what's going on. The complete that progress from quite to the left, quite to the right, that we don't fully see because of these DFT artifacts. Not surprisingly, I would say. So you will probably agree with me that the transport calculations will probably, if they rely upon DFT, will probably suffer from similar DFT-related, functional-related problems as the electronic structure calculations that you do otherwise. So that also reflects here. Good. So that's the summary. Transmission for gold much larger for silver. Here, transmission much more similar. And presumably, if we would have a better function, then we would even shift below, and we would actually get what the experimentalists observe. Good. That was one very recent example. So now, kind of standard. This is what we do a lot in this field with the experimentalists. Another example, not quite as standard, supposed to follow now, and that's about Oligocene wires. These wires have kept quantum chemists busy for many years now, and we have a funny prediction for the conductance to make in this context. Let me first tell you how we actually found these oligocenes to be very interesting also for theoretical physics. So originally, these things were discussed in the context of material science, for instance, by Massari and others, and they were suspected to be good for photovoltaic applications, with the idea that there's a band gap, and the band gap changes with the length of these molecules, and you could perhaps by change the proper length, adapt it to, let's say, solar light, and so on, produce efficient photovoltaic compounds. As far as I know, this idea has never really been put into practice, and at least not into commercially available products. But originally, okay, that was how we went into this. And not only we, also the Weizmann group, Oriental and his people went into this and measured how the conductance of this molecule depends on the length. And what he found was that the length is actually, the conductance is increasing with increasing length, not decreasing. You might somehow think that, okay, there's a wire, and the wire goes longer and longer, and the conductance should maybe go down. This is what would happen in usual metallic wires. This doesn't happen in quantum wires. You can have it the other way around also. And our job, we made it our job, let's say, to understand what's going on there. So we choose, first do a different type of contacts arrangement to compare to each other. So there's such an arrangement which we call short, and this is such an arrangement that we call long. We once again calculate the transmission function. We find a very nice Lorentzian, but the width of the Lorentzian now and the position of the Lorentzian with respect to the Fermi energy depends a bit on how we couple, which is probably not surprising to you. If we couple like this, then the transmission is a bit smaller because the Lorentzian is more narrow and it goes further away from the Fermi energy. While if we couple like this, then the Lorentzian is a bit closer and also a bit wider. So now the question is, what happens in the experiment? In the experiment, we saw that the transmission goes up. So we were trying many, many different calculations, comparing different structures with each other. And what we found theoretically is that we can kind of understand the transmission if we assume that there's such a short way through the molecule, not such a long way. In the long way, we don't get an increase. The transmission looks more like this. in the short way, we do get an increase. The transmission looks like this. Please don't be confused about all these data points over here. The data points just reflect our attempt to do a finite size and extrapolation with respect to the electrode size. So you see many data for many different electrode sizes. The best one, of course, is the biggest one, which is the fat symbol, the fat square here and the fat diamond over there. Yeah, so this is what the theory would predict. It should be this type of contact conversions prevalent, and once we told the experimentalists what to look for, they actually measured, looked at the measurements again. They kept pulling at the molecule. They did then a statistics of the pulling length versus the transmission. And what it turns out, by and large, is that what we predict here is very consistent with experimental findings. Good. So in this way, we can understand how the transmission, or we can at least reproduce the growing transmission. And now comes a twist. So at this point, we just did the quote-unquote just the transport simulation. And now I will give you a way of thinking about the transport simulation. And that's usually most of the fun. So here's a way of thinking about it. I plot for you the different transmission functions as we get them using such a geometry for molecules with increasing length. So the increasing length, they have funny names. So benzene is 1 ring, naphthalene 2 rings, 3 rings, 4 rings, 5 rings, and 6 rings. And what we get is a transmission curve that has a very nice systematic flow with a number of rings. If the number of rings grows, then the peak moves closer to the Fermi energy, and the width becomes more and more narrow. Okay. Anything to be understood about this question mark? The answer is yes. There's quite a few things here. Number one, let's focus on one of these resonances and actually not plot the transmission resonance. Let's just plot the local spectral function. You may remember the local spectral function is something like the density of states. And here we take the density of states just on the molecule. So you get also such a spike. This local spectral function has a piece, a low energy piece that overlaps with the occupied states. So this is actually sucking up charge. And if we integrate this, then that will just tell us how much charge is actually sitting in this molecular orbital. And now what happens in this flow of this DFT transmission function is that there's an associated flow in the spectral function, and the amount of charge that sits on the molecule will eventually converge to a finite number if we go into the long molecule limit. So there's an amount of charge that goes here, and if I make the molecule longer and longer, then the charge will no longer grow because of an interaction of the charge on the molecule with its image charges on the leads. That will be the type of physics that we have here. And now why does the transmission saturate? You see, saturation of the transmission means that this point here intersecting with the Fermi energy moves up and up and up, but not arbitrarily until this point, but until this point. And that point is actually controlled by the amount of charge on the molecule, and that has something to do with Friedel sum rule. So there's a Friedel sum rule that associates the charge on the molecule with the conductance. If the charge saturates, then also the conductance saturates, but it doesn't have to saturate to 1. It doesn't have to saturate to half filling here with respect to the state. It can be anything else. And what we actually extract now from our calculation is the amount of charge that eventually sits on the molecule in the limit where the molecule becomes very long. Good. So now I would like to share one more element of evidence of this little molecule here. It has one more interesting feature, namely, and a feature that has been already discovered by Evers and Chapman in '83, and again a feature that will also bring us down to a transmission prediction for a transmission measurement that has not yet been done for this molecule in the limit of very large length. So far I was talking about short length, and now I will tell you what we expect if we make it longer and longer, beyond what I was just explaining to you on the previous slides. And this physics has to do with the fact that there's this coupling matrix element T double prime between this and this site if you introduce a Huckel description of this. So what happens is the following. Suppose we don't have a Huckel description of this molecule, but only nearest neighbor hopping, no hopping from this guy to this guy. If you have only nearest neighbor hopping, then there's a kind of a conduction band and a valence band. And the funny thing is that these bands touch over there. So this is like an accidental degeneracy at these edges. And now if T double prime is introduced, that was also realized already by Evers and Chapman, then these two bands shift with each other. This guy goes down and this guy goes up, so that there's such an intersection point. And now what you can understand is that in the presence of such an intersection point, away from the symmetry points of the Brillouin zone, then the gap as a function of length of the molecule is something that strongly oscillates with the length of the molecule. There's a simple zone folding argument that actually supports this. So the prediction is, if you make the molecule longer and longer, the length should be about 10 or 15 or 10 or 12 maybe. Then there's a decay of the gap almost down to 0, and then it reemerges and it decays and it decays. So far we have just been touching with the experiment that I was discussing this regime, but not yet this regime. And the prediction is that if we would make this system much longer due to this zone folding type of argument, we would find a conductance that goes like this. It goes here. Eventually it looks a bit like it would saturate. But then if you go further to even longer systems, then there's a cut. It drops sharply and you start away from 0. Good. So far, transmission calculations for reasonably motivated molecules. What else can one do? And now this what else, I will just stop to be explaining too much. I just want to give you a few impressions so that you can see that IV curves are by no means the only thing that we can look at. These three gentlemen have been the main protagonists of the short story that I'm going to tell you now. So this is the object we are familiar with by now. There's a Green's function without leads, and then we couple the self-energies, we get the Green's functions. We can calculate the transmission as we want to before. Then we can also calculate this object, so the same thing, G and gamma L enter, also here, into this G smaller. And now I mentioned G smaller because if I have this matrix G smaller, then I can in a very simple way calculate the local current density. So I can really not only study the IV curve, I can actually show how current flows through molecule at each spot in space. And not only this, I can calculate the associated magnetic fields that have to do with the current flow and so on. Let me just show you pictures. So how it looks like if current flows through molecule. This is an armchair ribbon, and how does the current flow through? Well, it flows in a funny way. So not in a homogeneous fashion, but rather it shows these sausages. Current flow through armchairs is in sausages. And the sausages live above the plane or below the plane. The current doesn't flow through right away. That's a simple example. Let me show you more spectacular ones. So this is, for instance, a graphene sheet. I told you we can also repeat the same type of calculations for graphene. It's a funny graphene sheet because we have functionalized it with hydrogen atoms. Each one of these red dots over there is associated with a hydrogen atom that contacts to a carbon atom over there. It pulls the carbon atom from the sp2 into the sp3 hybridization. So it's quite an effect. And now let's just see how current flows through such graphene ribbons. That's a pattern. So the current comes from the top and it flows to the bottom. And what you can see now is a lot of complicated patterns. There's red color over here, and there's greenish color over here. The important thing to keep in mind is that the average current is about here. So this is something like turquoise. So most of the time here, there's the average current. But then if you go to the red region, the average current, the current in the red region is about 100 times larger than the average region. Actually, this is not the most spectacular example I have. If I replace the hydrogen by OH groups, then the difference between the average current and the current in these eddies, so these are eddies, is 3 orders of magnitude. So if you look, that's the statement, if you look how the current flows through these graphene sheets, then the typical current is 3 orders of magnitude lower than the currents that you would find in these eddies, and these eddies are not rare events at all. That's something I think very spectacular, and you can see this only if you have this type of transport simulations. These are the associated magnetic fields. The fluctuations with the local magnetic fields are really considerable. They can be 100 millitesla or so related per volt related to these current fluctuations. There's one last word that I wanted to say, one last outlook about current flowing in the presence of spin-orbit interaction. Suppose we would have spin-orbit interaction, then the Green's functions, as almost every indicator of the system, will also now carry the spin signature in a non-trivial way, not just a factor of 2. We can easily generalize the formalism that we had before. Let me not go through the formulas in detail. It's just supposed to illustrate. It all looks similar to what we had before. In particular, we can calculate also spin flip conductance, which is related to the probability that I come in with spin up. Then there's a spin orbit scattering. spin orbit interaction in the molecule or the molecular film, and that introduces a probability that I leave the film with spin down again. So that's something that one can calculate. We actually calculated it for such a armchair ribbon in the presence of one hydrogen atom. This is how the magnetization looks like in the mean field picture. And this is the effect that you get on the transmission curve. Here you can see this blue line. This is the transmission probability for spin flip scattering. And what you can see is that it's not so low. We only had one hydrogen atom in the system. And what we get is a transmission, the spin flip probability of about 1%. Now, what is the significance of this result? You may know that graphene is also a material that has been at least suspected to be interesting for spintronics applications. There were always difficulties using it for spintronics really because the spin relaxation rate is very high, and the question was, what is the physical origin of the spin relaxation rate? And then what people figured out, also we in this kind of study, is that it's very likely that spin relaxation has something to do with add atoms that locally promote a carbon atom from sp2 to sp3. Once the symmetry is broken, the spin-orbit interaction is enhanced, and that leads to a relatively big spin-orbit scattering rate. Good. So there's one more slide, and then I'm done. This is about the outlook. So I'm still not at the end of what one can do with these formalisms. What is under development at the moment are formalisms that calculate things like current-induced forces. So if a current flows through a molecule or just any material, it actually gives rise to mechanical force. That's a little bit related to electromigration, and one can calculate how big it is. One can hope to drive molecular machines with this force. There's also a force related to the spin flip probability that's going to induce spin orbit torque. That's what we try to calculate at the moment. And then one could go, of course, beyond DFT. One of the big dreams is to do fully GW-based transport calculations, where not only the molecule but also the leads are dealt with GW. And now I think the most recent developments in AIMS and also, for instance, in Turbomole with really efficient GW counts actually allow us to do this, which means that we hope that we can remove some of the transport artifacts related to DFT, functional artifacts, by just doing transport with GW. So there's a lot, I think, to be expected from this type of field in the next couple of years. I thank you very much for your attention.
Thank you, Ferdinand.